Welcome back. Let's talk all about reliability and validity. So, reliability and validity, which is classical test theory, are ways of evaluating psychological tests and measures. So, reliability is the consistency of the items within the measure. So, all the items should be related to one another within the measure if they're reliable. And then the measure over time. So, answers should correlate strongly over time. If I measured you on something at one point in time and I measured it at another point in time, if the measure is reliable, the output should be largely the same unless there's other extraneous factors influencing it. For example, the time is a factor that could influence the results. Validity is about whether the measure actually measures what it is intended to measure. Yeah, sorry, I can't say that any better than that is. So it's really about whether the measure actually measures what it's intended to measure. So, are you measuring what you intend to measure? That's the focus of validity. So that's reliability and validity. What are the differences between the two? Well, reliability is generally thought to be necessary for validity, but it doesn't guarantee validity. So, in practice, a test of a relatively changeable psychological construct, such as emotions, may be valid, but not particularly reliable over time because emotions are likely to fluctuate. Another example is say some tests we have of cognition. Over time, the test itself of cognition may be valid, but over time, the results may not be as reliable because cognition changes over time in young and old adults and middle-aged adults. So these are the key takeaways in terms of understanding that reliability is generally thought to be necessary for validity, but it doesn't guarantee validity. And a reliable construct can be valid. A relatively changeable construct can be valid, but not particularly reliable. So here is an example of reliability and validity in action. So the way I want you to think about these targets is that in fragmented statistics, we often think that there's a true value, right? So if we were to take the average height of everyone in the world, there would be a true answer to that question. And then we take a sample, and a random sample, and we use that to infer the height of the population. Now, in the same way, what I want you to think of in this bullseye is that middle bullseye is the true value for the population. So that middle bullseye is the true value of the population. And so when we look at something, say in the bottom left cell here, we can see that it's very reliable, right? We're measuring height over and over and over again. We're getting very similar results each time we measure it, but it's not valid because it's not we're not measuring what we intend to measure, which is the true population height. So this is a highly valid but not reliable test. In another instance, in the top right here, this is a case where something is unreliable. Every time you measure it, you're getting different results, but it's valid because you can see the dispersion of results whilst it's spread out, the error is sort of evenly spread around that true value. So you can think of it as the validity of the assessment. It's measuring what it intends to measure, just the measurements are not reliable, so you're not getting the same result. Here in the top left, you can see it's not reliable and not valid because it's not reliable because you're getting different results every time you're measuring it. And it's not valid because we know the true value is here and there should be an even dispersion around that true value for it to be valid. Right now, it seems to be skewed towards a part of the sample. And then here is the example where it's reliable and valid. You do a measure over and over again, you're getting similar results each time, and that measure is representing what it intends to measure, the true value. So that's reliability, validity. I think that is probably the best way to conceptualize it and understand it. But for some more examples that are a bit more intuitive, is reliability is a car which starts every time is reliable. A car which starts sometimes is unreliable. Validity is a car which always reaches the desired destination is valid. A car which misses the desired destination is not valid. And what the mapping onto statistics here is the fact that the validity is, are you testing what you mean to test, or is the measure measuring what it intends to measure? And then reliability is, are you getting the same result each time you start that car? Excellent. So that's reliability and validity. They're not inherent characteristics of measures. They are affected by the context and purpose of the measurement. For example, a measure that is valid for one purpose may not be valid for another purpose. Specifically, a test designed for adults and applied to children. And it may not even be as clear as this. You may have a measure that's designed in one cohort, but it needs to be validated externally in another data set. It may measure what you think it measures within that cohort, but then you apply it to another cohort and doesn't measure what you think it measures. And that's because of the nature of the context and the characteristics of the sample. So it's really important to ensure when you're creating a measure, you think about it within the context of what it's been created. In this instance, it's within the scope of adults. And if you want to make generalizations beyond that, you have to ensure that you're validating it appropriately. So in this case, it would be testing it in a population of children and seeing if you get the same results as you do for adults. So what are types of reliability that we have? Well, so I've noted here it's for reproducibility or consistency of measurement. So the types of reliability we have are internal consistency. This is correlations among multiple items in a factor. So we have a factor, we have items that load onto that factor. For them to be reliable, they're correlated, those items, and we can use convex alpha as well as a measure there. We have test-retest reliability, so the correlations between tests at one time and another point in time, and we can use Pearson's product moment correlation coefficient to check that. And then inter-rater reliability, the correlation between one observer and another. We can use Kappa's test for that. So these are the types of reliability that are available to us. So let's talk about them in more detail. So internal reliability or internal consistency it refers to how well multiple items combine as a measure of a single concept. So the extent to which responses to multiple items are consistent with each other. So how do we assess this? We have things like split half reliability, odd even reliability, and Cronbach's alpha. So we'll go through each of these step by step now with an example. Before that, an important point to note before we talk about interrelations between items is that if dealing with a mixture of positively and negatively scored items, we have to remember to recode so that all items are measured in the same direction. So for example, if the items are reflecting beliefs about brain health, then we want to make sure that all of the positive values indicate more belief in brain health or like behaviors for positive brain health, and the negative direction indicates belief in negative behaviors impacting brain health. So the key thing is that they all need to be scored in the same direction before we start talking about the correlation between them. Otherwise, all of this will have some feature within it which won't allow interpretability or for it to make sense. So we talk about split half reliability. What is that? Well, essentially, you sum the scores for the first half of items, and then you sum the scores for the second half of items, and you compute the correlation between the sums of the two halves to see how closely correlated they are to one another. So let me give you an example of this. Here's 6 items on a questionnaire that says it's okay to have, if some groups have more of a chance in life than others, inferior groups should stay in their place. To get ahead in life, it is sometimes okay to step on other groups. We should have increased social equality. It would be good if groups could be equal, and we should do what we can to equalize conditions for different groups. So if we were looking at this item, or all of these items, and we wanted to assess the reliability of these items, we could correlate the scores between 1 and 3. So we add up the scores of 1 and 3, and we correlate that with the scores of 4 and 6. So you can also correlate scores using random items. So say 1, 2, and 4, and 3, 5, and 6, just split half reliability. You split the sample and the items into halves, and then you calculate the correlation between them. Odd even reliability is similar design, but different concept in the sense that it's, similar concept, slightly different design, in the sense that you sum the scores for the odd items, sum the scores for the even items, and then you compute the correlation between the sums of the two halves, right? So in the first one, you just sum the first half of items, sum the second half, compute the correlation. And then the second odd even reliability, you just sum the odds, sum the evens, compute the correlation. The concept is the same. Foundationally, we're trying to say, are the items within these measures correlated to one another? If they're if they're reliable measures, they should be measuring the same thing. We should get the same result. And so they should be highly correlated. So odd even reliability in this case would be to correlate scores between 2, 4, and 6 with 1, 3, and 5, and then we get the odd even reliability. So what's Cronbach's alpha? Well, it averages all possible split half reliability coefficients. It's really important to remember. So when we talk about Cronbach's alpha, all it's doing is it's averaging all the possible split half reliability coefficients, akin to a single score which represents the degree of intercorrelation amongst the items. So most commonly used indicator of internal reliability is Cronbach's alpha. So you'll see it a lot, and it's essentially looking at the degree of intercorrelation amongst the items. So it's really important to get a sense of how correlated the scores are to one another. We use Cronbach's alpha. So when using this Cronbach's alpha, as a reminder, it's all possible split half reliability coefficients averaged out. What is a good value? Again, rules of thumbs are available. Less than 0.6 is unreliable, 0.6 is okay, 0.7 is good, 0.8 is very good and strong, 0.9 is excellent and greater than 0.95. It's actually too much of a good thing. It may be overly reliable or redundant, depends on what's being measured. And what I mean by that is if you have items that are perfectly correlated with one another, then by definition, they're actually measuring exactly the same thing. So what we want for them to do is to be contributing together to the measure of a construct and not the question that's worded slightly differently in the same way that's measuring the exact same thing. That's when you get perfectly correlated constructs. So we want to aim between 0.7 and 0.9, but keep in mind the scale length with this. So back to exploratory factor analysis. How many items per factor? Remember, I mentioned that the more items you have, the greater reliability. That's because the more items, the more rounded the measure. Really, the minimum number of items that you need to create a factor is 1. If you have one item that contributes to a factor or loads onto a factor, then that's all you need. There's no way to tell how reliable a single item factor is. But there's no maximum. So there's a law of diminishing returns. So each additional item will add less and less to reliability, but there's no maximum in terms of the number of items that can have. But typically, approximately 3 to 10 items per factor are used. But the final decision is subjective and depends on the research context. So if you have a factor and it has 12 items to it, and you look at the ones that are contributing least to the loading onto that factor, but they're still they mean a lot in terms of their interpretation, and you think that theoretically there's a good reason for them to be kept in. There's no reason that they can't be kept in despite this 3 to 10 items per factor rule of thumb. So it's about using the interpretation there. Typically, you're looking at somewhere in the ballpark of 3 to 10, but it's not always the case. So let's do reliability analyses. So here's an example using simulated data of subjective a survey with 5 items that are looking at subjective memory concerns. And I want you to note here, so the 5 items are someone forgets names of people, misplaces everyday items, lose track of conversations, forget why they entered a room, or struggle to recall recent events. So what I want you to focus on is Cronbach's alpha here, which is 0.926. And so we have, they're all very well correlated with one another. But when we look at Cronbach's alpha, if the item is dropped, then what we see is actually it doesn't change much. It doesn't improve and it doesn't change much when they're dropped. So because dropping the item does not change Cronbach's alpha, we wouldn't drop any items in this instance. Let's look at another example. Again, simulated data. This is attitudes towards healthy brain aging. And we have physical activity supports brain health, cognitive activity supports brain health, good sleep is important for brain health, brain aging is completely determined by genetics. Managing cardiometabolic health supports brain health. Now, if we look at Cronbach's alpha, if item is dropped over here, the far right column, you can see that, well, the total Cronbach's alpha is 0.782. And you can see it doesn't improve if you drop item 1. It doesn't improve if you drop item 2. Item 3 doesn't improve. Item 4, if you drop it, does improve from 0.78 to 0.88, right? So it's quite a big improvement there. And item 5, we remove it, it doesn't improve. So the scores on item 4 do not correlate well with the scores on other items, and the removal of item 4 does improve Cronbach's alpha. So item 4 being brain aging is completely determined by genetics. And so again, coming back to the items, if you pull apart the meaning, you can see that 1 to 3 and number 5 focus a lot on the person's control of factors improving brain health, whereas the 4th one is very much of a different opinion that genetics, brain aging is completely determined by genetics. So you can see how those are incongruent thoughts with one another, because one is focusing purely on these modifiable behaviors, and the other one is a belief of it's all non-modifiable. And so when you remove that item from the factor, your Cronbach's alpha will increase by 0.8 to 0.883. Excellent. So my question to you now is, I've created this sheet which has 7 items, and I want you to look at Cronbach's alpha if the item is deleted, and ask yourself the question of which item would you delete here? Yeah. So pause the video, have a look. Which item would you delete here? So you can get a sense, you don't have the total Cronbach's alpha, but you can get a sense that across all of these, with number 5, item 5, the alpha, if the item's deleted, goes to 0.8. So this is probably the biggest candidate for removing an item. So the answer here would be item 5. Okay, have another go at this one, a different scenario. Which item would you delete in this instance? So have a look at 1, 2, 3, 4, 5, 6, 7. And I don't know why I'm pausing, because you could always pause the video. Which items would you delete? It would be items 2 and 7, because you can see 2 and 7, it produces results that are around 0.88. So it increases Cronbach's alpha to 0.88. But you wouldn't do this immediately. What you'd be doing is you'd be looking at items 2 and 7, looking at all the items that are there. Which ones, here we can see removing 7 is actually a greater contribution to Cronbach's alpha, but I'd also be looking at the interpretation of what that item is. So what does item 7 mean in the context of 1 to 6? And does it make sense to remove 7, or is there a stronger theoretical rationale for removing item 2? And so I would use that as the focus for what needs to be removed first, see how Cronbach's alpha improves, and then see if it needs to be, another item needs to be removed from there. So what if you have a really short scale? So the 0.7 threshold for the alpha may be really hard to meet with a scale that just has 3 or 4 items. I've given you examples where the items numbers have been around 7 for each. So sometimes short scales are accepted as reliable if they have an alpha around 0.6 by checking the item rest correlations, right? So the 2 rules of thumb is the item rest correlation should be around 0.5 and above. Strong correlations between items belonging to the same scale, right? And the item rest correlation should be between 0.2 and 0.7. So there's 2 different rules of thumb. Ultimately, it gives you a sense that the item rest correlations need to be between 0.2 to 0.7 or 0.5 and above to get a sense of the reliability of that scale. If your factor has only 2 items belonging to it, then it's not appropriate to calculate a Cronbach's alpha. So instead, check the correlations between items and just report this. So you have what's the correlation between these 2 items, and you would report that. You could expect items to be moderately or strongly positively correlated around 0.5 or above. But again, I'll emphasize the point that at the end of the day, if you have these items, you think that they load meaningfully onto to form this factor, and the factor is interpretable. Even if the correlation is 0.4, there's reason to say that perhaps it can be retained depending on a whole host of other factors. But what I'm trying to emphasize is theoretical interpretation is really important in addition to the statistics. Um, Excellent. So let's talk a bit about validity. So that was everything to do with reliability. We talked about the Cronbach's alpha, odd-even reliability, split-half reliability, and internal reliability and consistency. The key thing I want you to take away, in addition from all of these, is that we use Cronbach's alpha because it's a nice measure of all the possible split-half reliability coefficients. But fundamentally, it allows us to get a sense of what is the reliability of our scale, and could we improve it with the removal of an item or not. Excellent. So that is that. Let's talk about validity now. So essentially, validity is, does the measure actually measure what it intends to measure? Does it measure the construct that you're hoping to measure? So validity is multifaceted. It includes comparing wording of items with the theory and expert opinion, examining correlations with similar and dissimilar measures, and testing how well the measure predicts things in the future. So all of these are different types, contributes to validity. So what are types of validity there? Well, the following is a list of the different types of validity ordered from easiest to hardest to demonstrate. So we have face validity, content validity, criterion validity, which is concurrent and predictive validity, construct validity, convergent validity, and discriminant validity. So we'll go through each of these right now. So, but that, I just wanted to have a summary slide show you all the different types of validity and to emphasize the easiest to hardest to demonstrate. So face validity. This asks the question, at face value, do the questions appear to measure what the test purports to measure? So this is important for respondents to feel secure and buy into the study. So how is it assessed? You just read the test items and you make a judgment as to whether it has face validity or not. Ideally, if you give it to someone else, they could also provide similar assessment of face validity and say, yeah, actually, it seems to measure what the test reports measure. Content validity is, are the questions measuring the complete construct? So it's important for ensuring holistic assessment, and how it's assessed is diverse item generation. So you have to do a literature review, theory, interviews, expert reviews, and that informs the development of the assessment. What happens when you don't have construct validity? Is it too many slides? Maybe it was a bit ambitious. You can get this first panel here, right, where you're not measuring the whole construct. You're just like sort of measuring a portion of it, and so as a result, you don't have that validity that's there. So to have content validity, you need to really ensure that the questions are measuring the complete construct through literature review, theory, interviews, and expert review. Criterion validity asks, can a test score predict real-world outcomes? And this is important for test relevance and usefulness. So how is it assessed? Concurrent validity is correlate test scores with recognized external criteria, present or past. So for example, political ideology with how they voted at the previous election, or offender risk rating with seriousness of the crime. And then predictive validity is a correlate test score with future outcomes. So for example, political ideology and how they vote at the next election, and offender risk rating with recidivism. And so so one concurrent validity is looking at present or past, and predictive validity is really interested in the future outcome. So correlating test scores with future outcome is predictive validity. Correlating test scores with current or past actions is concurrent validity. And so that's really the components of criterion validity. Construct validity is asked, does the test assess the constructs it purports to? So the truth, the whole truth, and nothing but the truth. Important for making inferences from operationalizations to theoretical constructs. So how is it assessed? Theoretical is the theory about the construct valid. Statistical, you can look at convergent correlations with similar measures. Other scales that measure similar constructs, see if what the differences are there. And discriminant, not correlated with other constructs as well. So you can have the convergence or the discriminants. The convergence is correlations with similar measures. other scales that measure similar constructs. That's the convergent validity. And discriminant is it's not correlated with other constructs. So those are the two parts of construct validities. And you can see it's just about sensing whether the measure itself reports the same results as others that measure the similar constructs and not correlated with other constructs. Those are the two key criteria. So those are the main things when it comes to validity. So now you have a good sense of face validity, content validity, criterion validity, concurrent and predictive, and then construct validity, convergent and discriminant. So let's talk about composite scores now. Composite scores are where you're combining item scores into an overall factor score, which represents individual differences for the target construct. So the new composite score can then be used for descriptive statistics and histograms, correlations, and independent variables or dependent variable in inferential analysis, such as multiple linear regression models and analysis of variance. So this is a really critical construct when it comes to understanding what we can do once we have a factor identified. We can combine the item scores, the scores on all the variables that contribute to that factor, to create an overall factor score, and that represents individual difference for the target construct. And then we can treat that as we would any other measure now. So then we can run our descriptives, we can do correlations with it, and we can put it into regression models. So now hopefully you can see the connection between exploratory factor analysis, how it can produce at the end of it a measure, a composite score that can then be used in multiple linear regression analyses, which we'll be doing next. So that's sort of the flow or connection of themes. So how do you create a composite score? So you may say, I have my factor, I have my 5 items that load onto my factor. How do I create this composite score that I could use as a measure? Well, there's unit weighting and regression weighting. So unit weighting is the average or total of item scores within a factor. Each variable is equally weighted. So you have your item level scores for each of your scores for each of the items in a factor. You add them all up and you divide it by the number of items that you have. So it's just the mean of all the variables that you have within that factor. How do you deal with missing data? We know that missing data exists, and so how do we maximize our sample size? Well, you can consider computing scores in a way that allows for some missing data, but in doing so, there are some important considerations I want you to keep in mind. So you compute a mean in Jamovi. So if you do it in the first way, where you say mean of these 6 variables, which all load onto a factor that you've determined from your factor analysis, this will give a missing value in any of, if any of the items have missing data. So if you run this in Jamovi, you'll get a missing value if any of the items have missing data for that participant. If you do mean in the same way, but you say ignore missing equals 1, this will calculate a mean for all participants unless they have missing scores for more than 1 item. So it's not a good idea if the scale is not reliable or if 1 item really can influence Cronbach's alpha. So, but if your scale is reliable and no item heavily influences Cronbach alpha, then you could adopt an approach like this where you ignore a missing. Another approach is to specify a minimum number of items. So if the minimum isn't available, then Jamovi will leave the composite score as missing for that participant. So these are all different ways of addressing it. I think the key consideration is if you're allowing for missing items from a participant within your composite score creation, first you have to acknowledge it, be transparent about it, and also consider, well, could that influence results unduly through that integration? Because you want to, in research, we really want to maximize the amount of data we have. And so if someone's provided responses on 5 of 6 items, but not the 6th, then we want to ensure we can use that, but not at the cost of biasing our results unduly or impacting the reliability through allowing removal of 1 item which influences our results. So how many items can be missed? You'll be not surprised at all that there's depends on overall reliability, but a rule of thumb can be you can allow one missing per 4 to 5 items, two missing per 6 to 8 items, and three plus missing for a 9 plus item factor. But please keep in mind, it depends on the overall reliability, right? So if in this instance of 4 to 5 items, if you know that you have one item which is unduly influencing the reliability of the scale, and you allow it to be missing in the computation of the composite score, then it can influence results. So it's fine if you don't allow any missing data and use the mean only for full cases. I think this is a fine approach in instances where you just allow it for when you have complete case data, at least at this level. As you go on in your statistics journey, what I mean is in this level for this course, but as you go on in your statistics journey, you'll learn about techniques such as multiple imputation. And this is where you can use the scores on other measures to impute or create the score on the missing data. And there's been lots of studies showing that this is a really robust measure, much more robust than imputing with the mean, which used to be done a long time ago in research, or leaving it as missing. But it goes beyond the scope of this course, but I just want to put that in your mind that there are other ways of addressing missingness in data, and multiple imputation is a really excellent way of doing so. So a researcher may decide to be more or less conservative depending on the factors, reliability, sample size, and nature of the study. Excellent. So regression weighting. So I've talked about mean weighting. Regression weighting is similar concept, but slightly different. So it's factor score regression weighting. It's the contribution of each item to the composite score is weighted to reflect the responses to some items more than others. So here are the weightings of each of the items, and you can see that the weighting on this fourth item is larger than on the second item, and so that's considered in the computation of the composite score for every individual's response for each of these items. So arguably this is more valid. You're testing what you mean to test through this measure because the composite score is weighting it based on what the factor analysis has said. But the advantage may be marginal. And the real challenge is it makes factor scores between studies more difficult to compare because if you use slightly different weightings, it's challenging. It's not a challenge if people publish their data. If they're able to publish their data, then it can just be reanalyzed with different weightings. But if you don't publish your data publicly, which is becoming more of a commonality these days for reproducibility, then it's not possible for others to be able to compare your results with other studies if you've used a weighting system. So Jamovi can calculate this for you from your exploratory factor analysis with weightings based on factor loading. So these weightings are based on what the factor loading is for each of the items, and that's how you compute the composite score there. Excellent. So that is factor score regression weighting. So this is why if you compute the correlations between composite scores in the exploratory factor analysis, this may differ from correlations between composite scores that you calculate using the mean scores because of the regression weighting. So that's the main thing to keep in mind there. So there are differences in how these are computed. One's weighted, the other is not, and that can result in differences in the results, but it shouldn't result in major differences. Excellent. So what we'll do now is we'll take a break, come back, and we'll do the summary of today's lecture. So stretch your legs, come back, and we'll go through the summary then.